Hi everyone, it's Sorkin. Today we have a problem when we are given an array. Let's say that array of 4, 7, 8, and 10. And we need to implement two functions, two methods. One is update and another one is sumRange. For the update, we are given an index and we are given a new value, updated value. For example, let's say that for index 1, we are given the value of 12. So we are updating for index 1, we are updating this value to 12. And another one is the sumRange. So we need to find the sum between the given indexes. So for example, let's say that we are given index 0 and 3, right? And we are updating the value, which is we are returning a value for the between 1 and 3, which is 28. There are several ways how we can solve this problem, and the easiest and the straightforward is that we are taking the value of the left index and then we are keep adding the values until we find the right index, value of the right index, and then we are returning the total sum. So in this case, the time complexity of this solution is of n. Can we do better than that? Yeah, for the sumRange, yes, we can do. Another method is that we can use a prefix sum. So we pre-calculate all the values before. So let's say, for example, here its values 3 plus 4 gives us 7, and 4 plus 7 plus 6 gives us 13, and so on. So in this case, the time complexity would be constant, but the problem is here that the update function is that for the update function, if we are updating the value, let's say here to instead of 4, we are updating the value to 10, then we have to update all the values that comes after it. So in that case, again, our time complexity would be of n for the update. So another method is that where we can achieve the time complexity for log of n for both, for sumRange and update, is to use binary index tree. So what's the binary index tree? So binary index tree, that let's start with the very simple. So for our array, for our initial array, right, let's call it nums. For our initial array, instead of setting indexes to values 1, 3, 4, 5, so we are setting the binary numbers for them. So we are setting a binary numbers, and we are constructing a tree based on the rightmost value of our indexes. So what's that mean? So for example, the rightmost value of our binary numbers, where the value is equals to 1, it's here, 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 and here, right? So for these values, we are just taking the values as it is. For example, for the first one, we are taking the value of 3. For the 3, we are taking the value of 6. For 5, we are taking the value of 5, and for the 2, we are taking the value of 2, and that is the kind of bottom of our tree, like lowest leaves of our tree, let's say. So 5 and 2. So what's the next one? Next one, we are taking where our second rightmost value is equals to 1. Second rightmost value, for example, it's here, and it's here. The value of it is the sum of the current value and plus the whatever comes before it. So for example, in this case, 3 plus 4 gives us 7. So right, gives us 7. And in this case, 8 plus here, it's 8 actually, yeah, it's 8 here. So 8 plus 12 gives us 20, right? So 8 plus gives us 20, so value is here 8. 20, and the last one is that we are taking where the rightmost value is third, right? So here we took the first one, so the second one, right, where the rightmost value is equals to 1, and the rightmost value equals to rightmost value is third, is here. The value for this one, all the values that comes before it, again, all the values we are calculating here, and it gives us what? It gives us 10. So it gives us 10. So, and this is kind of our binary tree. It's not exactly the binary tree, but so it looks like a binary tree, so resembling a binary tree. So what we do here, so how it's going to help us to achieve log of n time complexity. So for example, let's take the sum is equals to 7, right? So what is the how we are going to calculate that? Sum is equals to 7, and for the sum for 7, the value for the 7 is 2, and we are taking the binary value of it. So we are taking the binary value of it, 0, 1, 1, 1, and we are flipping the last set bit of it. So for example, in this case, we are flipping this one, gives us 0, 1, 1, 0, which is the value of 6 plus 12, and the plus we are again flipping this value, which gives us 0, 1, 0, 0, which is this value, plus 10, and in sum gives us 32, which is the sum of 7, right? So, and we are flipping the last one, which is 0, and the 0 is equals to 0. So, and we are going to, for the range sum, we are going to calculate the right sum and the left sum. And in both of these cases, the time complexity is log of n. So it's a 2 log of n. We can take that as a log of n. So this is the sum, right? This is the sum function. And how about the update function? The update function, let's say that we are updating, let's say the value of 2 to 11, right? Value of 2 we are updating to 11. So what we do here, first thing that we do, we are updating the value itself in the nums, right? In the nums we are updating value to 11, and the next step is that we are taking a difference. The difference is 11 minus 4 gives us 7. So we are changing the value first here to 7 plus 7 gives us 14, and we are doing exactly the same operation as we did before. Now in this case we are not flipping the last set bit, we are adding the last set bit. So we are adding to our what's our binary number here? Our binary number here is 0, 0, 1, and 0. So we are adding the last set bit, and our now value is 0, 1, 0, 0, which is here, right? So which means that we are going to also update the value here. We are also adding the 7 here, right? We are adding our difference. So 11 minus 4, we are adding 7 here, it's 14, and we are adding 7 here, which is now 17. And also again, our update function, the time complexity of our update function is also log of n. First thing that we do here, we are creating two variables, nums and bit. For nums, we are setting our initial array, and bit is our binary index tree. So we are taking the size of it as nums length plus 1, because our binary numbers start from 0, not from 1, and that's why we are setting plus 1 here. So the next one is we are populating our binary index tree. So for each index we are passing the value, and in our update bit method or function, what we do here, so we are incrementing index right away, because again our binary our bit array starts not from 0 but starts from 1. So we are updating the value, and the next one is that we are adding the last set bit, and we are doing this operation and propagating the value, adding to all other indexes until our index exceeds the bit length. Another one is that our sum range function, what we do in our sum range function. So we are calculating for the right sum, and we are calculating for the left, and again for each one it's log of n. And in total the time complexity is 2 log of n. We can disregard the 2 parts, so it's a log of n. So what we do in the get sum function, so in the get sum function we again incrementing index right away, and we are adding to our sum the values from our bit index array. So we are adding, then we are flipping our last set bit, and we are adding the next value until our index is more than 0, and we are returning sum. In our update function, it's the same as we have seen earlier, right? We are taking a difference, and we are updating our nums index with the initial value right away, and then we are adding the difference. We are adding to all indexes in our binary index tree. So we are calling again the update bit method that we have seen earlier. Okay, what's the time and space complexity of this solution? Again, the time complexity is log of n for both function, for update and the sum range. And the space complexity is determined by these two data structures. In both of these cases, the space complexity is, they are taking n values. So the space complexity is 2 of n, so we can take it as space complexity as O of n. Okay, that's it for today. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.